I'm Li Qiangli from Tianjin University. Welcome to our series of virtual academic seminars to celebrate the launch of Smart Mind. Smart Mind is an open access journal co-launched by William and Tianjin University. I'm one of young editor members of Smart Mind. The editor-in-chief of Smart Mind are Professor Wenping Hu from Tianjin University and Professor Hua Zhang from City University of Hong Kong. Today, Professor Paolo Samir from University of Strasbourg will give the presentation. Now, I would like to briefly introduce the speaker first. Professor Paolo Samir is a distinguished professor at the University of Strasbourg and the director of ISS. He has obtained a master's degree in industrial chemistry at the University of Bologna in 1995. In 2000, he has received his PhD degree in chemistry from Humboldt University of Berlin. He has been the permanent research scientist at the Institute for Organic Synthesis and Photoreactivity of Bologna from 2001 to 2008, and the visiting professor at the ISS from 2003 to 2008. He has published over 370 papers. His current research activity comprise chemistry of two-dimensional materials, smart supermolecular systems, as well as high-performance multifunctional materials and the nano devices for energy sensing and optoelectronic applications. Today, Professor Paolo Samir will give us a lecture about the molecules enabling multi-responsive and high-performance two-dimensional optoelectronics. Let's welcome Professor Paolo Samir. Please, thank you.
Great, you can see everything. Fantastic.
Yeah, I can see.
So, first of all, thank you very much, Li Qiang, for the very nice introduction. And I'd like to thank Professor Hu and Professor Zhang for the invitation. That's really great to be here with you. Unfortunately, I'm not there physically. That is what I would have loved to be. But given the time constraints that we have due to the COVID, this is not possible, as you know, but it will happen soon. So as soon as we get rid of all this, I promise I will come physically to Tianjin because it's a great place, great people, and so I'm looking forward. Now, in the meanwhile, I think science has to continue, and that's unfortunately the way to do it is remote via this kind of video conferences. And this is what I'm going to do today. I'm going to show you what we do in my laboratory in Strasbourg in the last few years. And we have a background of molecular scientists. So we have been working a lot on organic electronics and molecular electronics in the past. And now we actually try to exploit what we learn with molecules and macromolecules and to use this with 2D materials. And so you will see that there are a lot of small tricks and approaches we develop that actually are very much inspired by what has been done in the last 20 or 30 years in organic electronics. But actually, I think is a great source of inspiration for doing something different with 2D materials, because it's true that most of the people in the business of 2D materials are coming from a different background. So they are coming from the, let's say, more physics background, and so they are not able to play with the chemistry of the systems as we have developed in the community of organic electronics. So let me start by just highlighting that graphene related to the materials has unique physical and chemical properties in terms, for example, of mechanical properties, optical properties, electrical properties, thermal properties. And this, of course, opened the door to a number of potential technological applications in a variety of technologies that can be, for example, in sensing, in security, in touch screen, in contactless and optics, in communication, in electronics. Therefore, I think here it's just a matter to try to identify the properties that we are looking for and try to foster these properties and integrate this in a real technology. So what I'm going to do today, I'm going to focus on, let's say, in general, on 2D materials, but more specifically on 2D dichalcogenides, in particular on the group 6 of transitional metal dichalcogenides. And of course, by their own, this implies molybdenum disulfide, for example, tungsten disulfide. Wait, let me put the pointer on. Just 1 second. Laser pointer. Okay. Molybdenum disulfide, tungsten disulfide, molybdenum diselenide, and tungsten diselenide. These are the 4 classical type of, let's say, compounds. Of course, by their own, they already possess a diversity in terms of structure, composition, and properties. But these are anyways, let's say, hard to be tuned or modified. And that's the way we come in with the combination of these 2D materials with molecular science, because this allows us not only to adjust the properties, the physical properties of these 2D materials, but also to improve them and to confer new properties, which is something that allows us to go towards multifunctionality. And so the chemistry of 2D materials is extremely rich. You can just look at the amazing work that is done by Professor Zhang, that is here with us, and see what are the infinite solutions that you can pursue as a chemist. Now you can choose any type of 2D materials. There are a number of different options that can go from transition metal oxide to amixine, to phosphorine, to TMDC, to graphene, to silicene, and then you can actually have them interacting at the covalent or non-covalent level with molecules or macromolecules. So that is what I'm going to present you today, our work. The first part is going to be about the covalent functionalization of transitional metal dichalcodenide, and in the second part, I use non-covalent functionalization. So the first part is actually focused on showing you that you can boost the electrical properties of printed 2D semiconducting films using an approach that I will call the network approach. And now everything is based on the fact that you have 2D materials are defective rich. So defects are, on the one hand, if you're looking purely on the electronic application, you can see some negative aspects related to defects. But on the other hand, defects are sites that are more reactive. And so as more reactive sites, these are ideal for any kind of controlled chemical functionalization. Now, this is what we have been demonstrating in 2017 with Simone Bertolazzi in a study that we took simply molybdenum disulfide that can be CVD, can be Scotch tape, and actually typically already in the pristine MOS2, every 10 by 10 nanometer, you have a point defect that is a sulfur vacancy. Well, this might not be enough. You might look for more defects, more vacancies, so that we, by using some well-known approaches, we exploited the ion beam of the X-ray photoelectron spectroscopy, so of XPS. And so by irradiating with argon beam, we could generate more and more defects. Of course, the generation of more and more defects also is accompanied by a lowering of the electrical characteristics of the CVD MOS2. And you can see here in the center how the mobility is decreasing. Well, actually, we just see here how the current is decreasing through the junction, or on the right, how the mobility is decreasing with the increase of number or defectiveness of our molybdenum disulfide. Now, the idea is that these sulfur vacancies, they can actually be replaced, they can be filled, so they can be healed with thiol molecules, okay? So the thiol molecule fills the vacancy, heal the vacancy. And so what we have been doing in this study is we have been using a simple commercial butanediol to, let's say, to heal the vacancy, the sulfur vacancy in MOS2, and this is reflected by the fact that we have gained back, so we recuperated or recovered the electrical characteristic of the pristine MOS2 to a great extent. Now, this is just a demonstration that thiol chemistry, which is well established for all this, the interaction between thiols and gold, can be useful in order to control the functionalization of MOS2. And so then it happened that I went to a meeting in Dresden, invited by Xilian Fang, and there I met Jonathan Coleman. Johnny Coleman from Dublin is a pioneer of liquid phase exfoliation of 2D material. And actually, this was in front of a beer in the evening, and we were discussing about the paper that he had just published in Science. That was about all printed thin film transistor from network of liquid exfoliated nanosheets. So he actually he took molybdenum disulfide and he printed this. And then actually I was a bit complaining with Jonathan with the fact that the mobility that he reported were quite low. And he argued that this was due to the fact that in the channel there is a lot of liquid phase exfoliated flakes of molybdenum disulfide, and there is very little interflake connectivity. So the charges don't pass from one to the next flake. And this is the bottleneck for charge transport. And so at that time, I have a new PhD student, Stephanie Polter, that joined the group. And so I decided to put him on this topic. And the idea is very simple. And again, we took a lot of inspiration from organic electronics. When you exfoliate 2D materials, the flakes you obtain can be seen as pieces of a puzzle. And then after these puzzle pieces are disconnected, and you can think about bridging them with other type of pieces that to create a real network. And actually what we have been doing is to take this liquid phase exfoliated MOS2 and use a doubly thiolated molecule that can act as a bridge. This molecule that we chose is the benzene dithiol, and therefore the core of the molecule is semiconducting. And so in this way, we can interconnect covalently the flakes to create a network. Now, on the same time, we not only create a network, but we also yield the sulfur vacancies that we have on the MOS2 type of surfaces. And so the way we produce our devices is the following. We start from ink of the MOS2 or other type of disulfide. Then we use some electrodes on silicon that have pre-patterned gold. So these are commercial ones. We spin drop casted actually the ink on the top of the electrodes. And then at this point, we put the film in a controlled nitrogen atmosphere. And then we place on the top a drop of the benzene dithiol. Now, what is very important is that this benzene dithiol is dissolved in hexane, because hexane induced a minimal doping effect on MOS2. And then we actually did this inside the controlled atmosphere of the glow box to avoid thiol oxidation, and in the dark to avoid the photooxidation of the thiols. And in this way, we produce some, let's say, networks where the flakes are connected like this. And so now let me just prove that this is what really took place. And so we do a number of characterizations to demonstrate the occurrence. The first characterization we did was X-ray photoelectron spectroscopy. On the left, I will put the film of disconnected MOS2 flakes, and on the right, the network. That is where the flakes are covalently connected. What you can see by focusing on S2P peak of the XPS spectra, that we have the substoichiometric component, this defective component, which if we pass from the film to the network, this decreased drastically from 5% to 0.5%. So we have decreased the number of defects. We also exploited Raman spectroscopy, and in this case, we have been focusing on the A12G and the A1G peak, and we saw that they narrow by 10% upon exposure to the thiol molecule, with a small blue shift and increase of the ratio between the two. And this can be expressed, this represents an information about the reduction of the defect density. So this kind of Raman spectroscopy was done in the group of Andrea Ferrari. So overall, we have less edge-terminated structure. We also have been studying by contact angle, and we observed that the film was hydrophilic and the network became extremely hydrophobic. And actually, this hydrophobicity is such that when we expose the films to water, in the case of the film, after a few minutes, there was a detachment of the film from the silicon dioxide, whereas the network was extremely stable. And this is very interesting for water-based application. Then, of course, we are interested to look at the electrical characteristics of this kind of network, and therefore we exploit a liquid-gated thin film transistor. And the reason why we use this instead of a standard back-gated device is because the dielectric liquid penetrates the free volume of the semiconducting film, and therefore we can take advantage of a volumetric gating effect. And without going to the details, the comparison between the network, the film and the network, we observed for the network an increase of 10-fold of the field effect mobility, a 10-fold increase of the ion-off ratio, and also the threshold voltage did not change, which indicates that we have an absence of doping effect. We also observed that the device switched much faster, of 10 times, in the network compared to the film. So overall, the figure of merit are such that we have an increase of 10-fold of the mobility going from film to network, of the ion-off ratio, and of the threshold of the switching time, whereas the threshold voltage remains the same. And so this kind of approach was actually demonstrated in that paper that it is generally applicable for disulfide, like tungsten disulfide and rhenium disulfide. And actually, we have good evidence that it can work also with diselenide, like tungsten diselenide, in which case also thio molecule can be used to heal vacancies. So the network display improved electrical performance and higher water stability and mechanical robustness. Now, of course, the question is whether the bridge that we use is important or not to get this kind of enhanced performance. And therefore, in a very simple study, instead of using a benzene core between the two thiol groups, we used a alkane. So we use a C3 type of alkane, so propane, and we observed that the increased performance are much, much lower when we use an alkane that is not semiconducting compared to the benzene. So what is next? What is next is actually that you can think of using this kind of networking approach to different type of 2D materials, depending on the type of application you have in mind. And actually, you can also try to change the type of bridge. Instead of a single phenyl, you can put things, for example, that can be used for other type of application like detection or sensing. Now, let me pass to the second part of my presentation. And what I'm going to show you is about a non-covalent functionalization. And here, we use this to develop some responsive optoelectronic devices. And so we, first of all, I will show you how we can make heterostructures that are responsive, that are based on 2D materials interacting with molecules, so as a way to foster multifunctionality. And this recently we demonstrated that can be done with the Janus approach by the asymmetric functionalization of the two faces of the 2D materials. And this is very interesting in the framework of a More than Moore in terms of functional diversification, laser miniaturization as a solution to CMOS digital circuitry. Now, we all have read about the beautiful van der Waals heterostructures that have been reported during the last 10 years, starting from the pioneering work of André Geim, as a way to, let's say, diversify properties into the materials by simply superimposing two different types of the materials and start rotating them in order to look at the periodic potential that can be seen in Moire pattern. Now, this is the approach of the physicist. If you are a chemist, what you do, you take any kind of 2D materials, and to modulate the surface, you literally deposit on its surface any kind of molecule that can be, for example, electron donating molecule, electron withdrawing molecules, to have a controlled doping effect. Now, what I'm going to talk to you now is about the mechanism of doping and how doping can be reversible. And I will show you the two most classical examples of mechanism of doping. The first one is the molecular dipole-induced shift of the work function that you obtain when you take a polar molecule and you physically solve this on the basal plane of 2D materials. And so what you have is that the dipole of the molecule emanates an electric field, and this behaves like a local gate that is capable to shift the work function of the 2D materials, and this induces a doping effect. Now, to do that, we use photochromic molecules that are small organic molecules that undergo isomerization between different states, which can be stable or metastable, and these states have different properties. So the most famous one are the isobenzene, which can be switched from the more extended E form to the more compact Z form, and reversibly, one can go from the Z to the E, either thermally or with a visible light. The two states have different dipole moments, or you can play with diaryletin. Diaryletin is a molecule that has been developed by Professor Iri in Tokyo. And diaryletin, the peculiarity that you can switch from the open to the closed state with UV light, and you can go back with visible light. The two states are thermodynamically stable, and they exhibit different energy levels. And so the idea is that we use photo-switching molecules entity as a gate to translate an incoming input that is light into a change of the material. Now, if you are interested in this and how you can apply it to the materials, we just last week, our large, let's say, extensive review article appeared in Chemical Reviews, which was a great, let's say, summary done by Professor Yuda Zhao. Yuda was an outstanding postdoc in the group that is now a professor in Zhejiang University. So let's start with to see how a molecule in dipole-induced shift in the work function can be used and to manipulate the charge carriers by a light-induced distribution of the molecular dipoles. And so the idea is that if you want to play with dipoles, the extent, so the magnitude of the doping depends on the mutual orientation of the dipoles with respect to the surface. And therefore, you can boost this effect by using collective effect and being able to align all the dipoles. And so the idea, this collective effect by a molecular sorbate is very similar to what you have in van der Waals heterostructure. So we are fabricating nothing else than inorganic, organic, hybrid heterostructure. And so we exploit the collective nature of self-assembly to convert the light stimulus, to convert the light-induced change in the single molecule level into a macroscopic change of the properties of the graphene or MOS2. And so you start from the 2D materials, that is your scaffold on the bottom, and you arrange these kind of small bricks, and these bricks are nothing else than pieces of Lego that are switchable. Now, how you can easily create this kind of super lattice, this is very simple. You can use long alkanes, because long alkanes, they have a high affinity for the basal plane of graphene and MOS2, and they form lamella structures. And these are actually super lattices. So they pack along the zigzag axis, for example, of the graphene. Now, so this work was done by Marco Gobbi, and the idea is that we took spiropyran with a long aliphatic chain. This R is nothing else than a C18, so octadecyl chain. And we took spiropyran because it can undergo isomerization from the spiro to the mero with UV light and can go back with visible light or with thermally. And the two states have a very different dipole moment. So these are ideal to actually use this dipole effect for doping and de-doping our 2D materials that is on the bottom. The presence of these long alkyl chains is such that force the molecule to assemble into a lamellar structure, so to create this kind of superlattices. Now, this kind of superlattices on the CVD graphene displays a photo switch induced by the isomerization of the spiroparent that we could see when we put this kind of, let's say, CVD graphene on quartz and spin coat the film of the photo switching on the top. And this has been studied by UV spectroscopy. If you look at a smaller scale, you can do scanning tunneling microscopy images, and then you can see that the spiral molecule, they form lamellar structures, and on the very small scale on the bottom, you can determine the unit cell of this lamellar structure. You can irradiate with UV light, and you trigger the isomerization from the spiral to the marrow, and then in this case, we can see that there is another type of lamella packing that is obtained. You can see that the unit cell of the spiral is different from the one of the marrow. And then if you wait some time or you irradiate with visible light, the adsorbate molecule, they undergo back isomerization to the spiral. And you can see this is observed by the same unit cell that you have here compared to the first column. Now, the occurrence of this isomerization is something that we can actually study also via modeling. Modeling showed, done in a group of David Bergeon in Mons, showed that the head group that is non-planar of the spiral doesn't pack firmly on the basal plane of the graphene, whereas the marrow that is more planar, it packs very firmly, and actually this is reflected by the previous STM image by a more, let's say, a higher resolution in the marrow, where the molecule are better immobilized on the surface, a more blurred image that you have in the spiral, due to the fact that the head groups are not very well packed on the surface. Now, the fact that we have isomerization on the basal plane of graphene, this is something that you can monitor also with XPS, because if you look here, you have in the spiral, the nitrogen is in the neutral form, whereas in the marrow, the nitrogen is in the positively charged form. And therefore, if you look at N1S peak, you can see that you have nitrogen in neutral form in the spiral. Upon illumination with UV light of the film, you have the emergence of this blue peak that is a fingerprint of the positively charged nitrogen. And upon visible light illumination, this blue peak, to a great extent, vanishes, proving that the reversibility of this isomerization of the spiral on the surface. This was done by Marco Nardi in Trento. Of course, we're interested in the electrical characteristics, and the idea here is that we spin-coated the spiral on the basal plane of graphene, and already you can see we can compare the pristine, so clean graphene device with the spiral. We have a small end-doping effect, you can see with the red curve. If you irradiate with UV light to trigger the isomerization from spiral to marrow, the end-doping effect is major, and you obtain the blue curve. But with visible light, actually, you recover this end-doping, and you go back to the initial spiral curve. So the spiral to marrow end-doping effect has a carrier concentration change that is quite large. It's 4.4 and 10 by power 12 centimeter minus 2. Actually, you can also fabricate lateral heterojunctions. And the way to do that is that you take a large crystal in the channel, a large graphene crystal, you spin coat the spiral on the top, you irradiate with green light the whole crystal. And so you bring into the marrow form, the blue one, all the molecules. And then you locally, with visible light, you irradiate only with green light, you irradiate a small part of the crystal. And this you can see here, the new curve actually has a part that reflects the spiral content and another one that is left over of the Mero content. So this is the lateral heterojunction. Now you can do the very same doping and undoping effect, also using as a underneath layer the MOS2 instead of graphene. And you can see the very same process of strong end-doping effect going from spiral to Mero, and the full recovery with visible light. So that is what you can do by fabricating some, let's say, heterostructures, hybrid heterostructure, and use the switchability of the dipoles in spiropyramid. Now, what I'm going to show you now is actually you can use also another process, another mechanism of doping, which is the charge transfer. And this is about energy level alignment that determines the doping by favoring the electron transfer of from the 2D materials to the molecule and vice versa. So that was a work done by Aixin Q. There was an outstanding PhD student that now is back to China in Shanghai Jiao Tong University, and under supervision of Dr. Zhaoyang Liu, who just came back to China a couple of days ago to get a professorship at Jilin University. Now, the idea is that as a 2D material with tungsten diselenide, and in the first study I show you, we use this in the condition where it behaves like electron transport dominant semiconductor. And we put on the top of the tungsten selenide about 3 to 5 nanometer thick layer, spin-coated of diarylethium. And diarylethium, as I mentioned before, has energy states that are different if it is in the open and the closed state. Now, given the conduction band of the tungsten diselenide, we have designed and synthesized in collaboration with Professor Stefan Hecht in Berlin, two different, let's say, one type of diarylethium such that is LUMO level. In the closed state is in the band gap of the tungsten selenide, and the open state is out of the band gap. And therefore, we can switch the diarylethium from one state to the other. And what I want to stress is when one dopant has a state that inside the band gap of the semiconductor, it will behave like a trap for the charges of the semiconductor. Whereas when the level is out of the band gap, the interaction with the semiconductor is purely electrostatic. And so this is what we have been doing. Diarylethium actually, by the way, is high fatigue resistance, high thermal bistability, and high phototunable energy level. So this is the way we performed the experiment. We first of all exfoliated the few layers thick tungsten selenide, and we transferred this to the silicon dioxide, fabricated backgated devices with a laser writer, and we deposit metal content on the top. Then we anneal this to remove all the residue of the resist that we've been using, spin-coated diarylethium, and then we perform the electrical characterization in the glow box under control light that can be either in the dark or under UV or visible light illumination. And so we start from the pristine type of tungsten selenide device. It's not an optimized device. So you can see mobility is not extremely high, but it's still not bad. Then we actually place Physisorb on the top of the diarylethium in the open state. And so we observe a minor p-doping effect with a minor decrease in the end transport and the electromobility of about 20%. Then at this point, what we can do, we can irradiate with UV light to trigger the isomerization from the open to the closed state. And you can see that this accompanied with a very strong reduction of the electron mobility of 50%. And actually, we have an increase of the threshold voltage. Then we can irradiate with visible light in order to bring the diarylethium back to the open state and stop this kind of charge trapping. And you can see that illumination with visible light, we recover fully the mobility, the initial mobility of 13, and also the threshold voltage is fully recovered. So we can modulate, by modulating the state of the diarylethium, we can control the current through the tungsten diselenide. Now, the curves, if you look at the output characteristics, the they show a ohmic behavior, and this indicates that we have a good contact with respect to the gold electrodes. And actually, we can make cycles by illumination with UV and visible light, one after the other, and we can modulate the current through a junction of 60% with an efficient trapping and detrapping of the electron. So we see a high robustness of our switching, so high reversibility and no degradation. Now, of course, we can try this to be used for memory, for applications. And so the idea in this very preliminary study was to start from the open state where the current is the highest. And then we radiate with UV light for 2, 4, and 8 seconds. And you can see that this allows us to trigger the isomerization of a finite number of molecules. First, we reach level 1, then level 2, then level 3, then level 4, after 16 seconds irradiation. Then we can irradiate with visible light and go back fully to the level 0. So with a high accuracy, we can write and read. There is a high retention time of our diaryletin. This can exceed also hundreds of days. We did in different studies. And of course, when you start irradiating a semiconductor with light at different wavelengths, you can wonder whether the effect of this change in the current was due to photoconductivity effect. And so to rule out the photoconductivity, we took the bare tungsten diselenide and we did the same experiment. You can see that when we radiate with UV light and when we radiate with visible light, in both cases, in the bare tungsten diselenide, we have an increase in the current. Whereas if you do this when you have the diaryletin that is physically solved on the valence tungsten diselenide, the UV light is accompanied by a decrease of the current due to the fact that we are creating traps in the channel. And with the visible light, we can actually increase the current through the junction. So the effect of photoconductivity is minor, and the role of this switching of diaryletin is the important one for observing the change in the current through a junction. Now, you can, of course, use tungsten diselenide also in the condition where it behaves like an bipolar transistor by changing the thickness of the tungsten diselenide. I have no time to go into the details. I'm just going to show you the approach that was based on the fact of using not only the diaryletin derivative that we use so far in order to trap and untrap charge transport at electron transport, but also we have designed a different type of diaryletin whose HOMO level are actually either in the band gap or out of the band gap if one considers the valence band of the tungsten diselenide. Therefore, we can also trap and detrap at the HOMO level, therefore the whole transport. And so we physisorb on the top of the tungsten diselenide a blend of the two diaryletin. And without going to details, you can see that on the same time, by illumination with UV light, we can reduce drastically the whole mobility of 96% and the electromobility of 40%. And then with visible light, we recover all of them by going back to the open state of the diaryletin, both for both type of diaryletin, the one that control the whole mobility and the one that control the electromobility. Now, let me spend the last 2-3 minutes on the very last result we have been reporting at the end of last year about the Janus approach. And the idea is that we wanted to exploit the two phases of the tungsten diselenide in order to expose them to a different local environment and therefore to control the property of 2D materials in two different manners. So with two different inputs. And the idea is that we place the photochromic layer on the bottom of the tungsten diselenide, therefore in between the tungsten diselenide and the silicon dioxide surface. And on the top, we use a ferroelectric layer. And so we use an organic ferroelectric material that is people in organic electronics like Vamping know him very, very well. This has been thoroughly used with inorganic electronics for fabricating a ferroelectric field effect transistor. And so we make a layer of these materials because that in the ferroelectric state of the gate insulator layer influence the surface potential of the interface with the semiconductor, and this can be used to control the accumulation of the depletion state of the charge in the device. And so also this approach is non-volatile. And so you can see that we have reported two approaches in two different papers. The bottom photochromic layer can be either a diarylating layer, like the one we showed so far, and or it can be a self-assembled chemisorb spiropyran layer that you see here, with a saline unit to chemisorb on the basal plane of silicon dioxide. And then we have tungsten diselenide, and on the top we put the same ferroelectric layer. So I will show you the details of the first approach, and then, of course, if the voltage that you apply in the case of ferroelectric materials exceed the coercive field, the dipole in the ferroelectric materials, they partially align with the external electric field, and this results in a permanent polarization. This polarization remains also when you remove the electric field that you apply. And so the magnitude of the polarization vector depends on the difference between the applied electric field and the coercive field, and the number of memory states in a ferroelectric cell can be increased if you use the intermediate polarization state that it can obtain by applying an external electric field with magnitude slightly higher than the coercive field. So in this way, you can access to different level states. And this is what you can observe here by sweeping the electric field. Now, first of all, what we did, we integrated our tungsten diselenide, and we placed on the top a 500 nanometer thick layer of our ferroelectric polymer in a capacitor type of device. And you can see that we can make over 10 cycle, and actually we can sweep the electric field, and we see an absence of fatigues in this triangular voltage sweep method that is currently applied. Now here, the device is for a multi-layer of diarylating, tungsten diselenide, and the ferroelectric polymer. First of all, I wanted to prove that we can still switch the current through the tungsten diselenide with light stimulus by changing the state of the diarylating, because in this case we placed diarylating underneath, and so that was not obvious it did work. But you can see here that we can actually change the state of the diarylating from the open with higher currents to the closed, and vice versa. And so then on the right, I will show you how you can have the electrical control over the switching. We start with the tungsten diselenide that is actually in the P down state, that is the one with the higher current, and then is obtained by applying a voltage of plus 6 volt. Then when we apply a negative voltage, we can bring all the dipole into the P up state, and the P up state, the electron current is decreased of about 68%. And when we then bring it back to the P down state by applying a plus 60 volt, we can recuperate fully the higher current through the junction. So this proves the electrical switching capacity of the device. Now we try in this slide to combine the two, which is the most important slide of this story. We start with the higher current, where we have the ferroelectric system in the P down state and the direct in the open state. And then in this case, we have irradiated with UV light, and we bring the directing to the closest state. And so we create some traps for the charges, and we decrease the current through the junction. Look at that the P is still in P down state, the ferroelectric. Then at this point, the polarization direction of the polymer was switched from downward to upward by applying a negative top gate bias of minus 60 volt. And you can see the current that we have further depleted the electrons in the channels. And so at this point, we have the lowest current possible. Then at this point, we use visible light to open from the closet to the open state diarylating, and we recuperate a bit of the current. Then we apply a plus 60 volt, and we go back to the P down state. So this is completely reversible. You can see that we have, we can use in, let's say, in a asymmetric manner, the two inputs. Now, let's see how many levels of, let's say, writing we have. If you use control the UV dose and you irradiate with a few second irradiation UV light, you can adjust the population of directly in the open, the closed state, and record 84 different levels. And actually, you can also use the electrical, let's say, writing in order to assess, let's say, the multi-level memory by recording in this way 9 different states by applying a voltage that is just a bit higher than 60 volts. So overall, if you sum up, you have 9 ferroelectric states and 84 photo-induced states. That brings you to 756 levels. So this is a 9-bit memory device. This can be further increased if you use a very fast laser, and you can start from, let's say, 10-bit memories for just light control. So with this, I'd like to finish my presentation. I hope you enjoyed my presentation and you had the feeling that molecules, they can be really an added value to 2D materials because they diversify properties. And this is very interesting for optoelectronic application in the framework of the more than more technology. So of course, we take advantage of our sponsor that in particular Europe, and actually we have a very interdisciplinary group that actually perform this kind of activity with a lot of chemists, but also physicists and engineers, because those are a bit more expert about device engineering. And I like to stress that actually my group consists of over 12 Chinese PhDs and postdocs who are doing excellent and hard work, very creative in my laboratory. Many are coming from Tianjin, from the Professor Hu group. So I'm very much looking forward to get more interaction with you guys, to get more students, more postdocs coming to our group, because actually this brought to us a lot of creativity and new solution to organic optoelectronics and to the optoelectronics. You can recognize many faces here that you already know. And with this, I'd like to thank you for your attention, and I will be very happy to answer to any of the questions you might have for me. Thank you.
Okay, thank you, Professor Paolo Samor. Thanks for your great talk. Now it's time for comments and questions. Any questions? Professor Paolo Samor, maybe I ask a question firstly, and
sure.
it's just very interesting and efficient idea to modify the optoelectronic performance of the two-dimensional materials. So by using some responsive molecules. So I want to know how about the coverage of the molecules. So you use uniform the film of organic materials, or just
yeah, absolutely. That's a very good point. So let's say I have using I showed two different approaches. There is a one. Let me go to the slide so I show you. There is here. Let me see. Okay. The one of the spiropyran, that is the one where we play with the dipoles. Actually, the fact that here you wanted to control the orientation of the dipoles, the best is to have a continuous monolayer that covers the basal plane on the surface. Because if you have a thicker layer, I think it will be quite complicated to have a full control over the orientation of the dipoles. And here, to maximize the effect, you really need to be able to control the alignment of dipoles. So monolayer thick super lattices. But differently, when this is the approach of the dipole, but when you play instead with the second approach, the one of charge transfer. Here, with the best condition that we use when we made the film out of diaryletin is to have a continuous film. And we noticed that the best was to target on a film thickness that is between 3 to 5 nanometers. Okay, and so here there is no effect of the orientation of the dipole. Of course, in a spin-coated film, the molecule are slightly more disordered, but we observed that the effect was maximized for this kind of thickness. But of course,
thank you.
It's very important to correlate to be able to have under control the thickness or structure of the film, of the organic film.
Okay, thank you. Professor Hu?
Paolo, thank you very much for your excellent talk. Yeah, I thought you in a lot of new progress in your group. Great.
Thank you. Well, because the students you send me are very good.
Thank you. I have one question about you. The first part, actually, you use the benzoyl disulfide to link the molybdenum sulfide flakes.
Yeah.
Yeah, I think it's very interesting. My question is, because now you just use this link is 1-benzoyl, and how about the possibility to change it as, for example, naphthalene or anthracene, or that means enlarge this 1-benzoyl to 2 or 3, or change it as a benzones. That means
also because exactly this is a very good point. We are working this direction because this you can also use light. You can make photo transistors. The only thing that one has to watch out is to remain with let's say molecules that are highly soluble in solvents that are as more as possible apolar, because when you start playing with the polar solvent, then this can become a strong dopant for the 2D material. Okay, and so that is the reason why here we have been using actually hexane. Okay, so as a solvent for the benzene diethyl. Of course, you know better than me that the more you create larger polyaromatic, the more aggressive solvent you must use. You know, like you use chlorinated solvent, and this is not too good. Okay, so one has to find the right let's say compromise, because the 2D materials are extremely sensitive to solvent that have a small dielectric constant. Okay, so we did a systematic study on solvent that you would have considered to be purely solvent, not dopant, but we found out that they strongly dope 2D materials like MOS2, like black phosphorus. So let's say that's the strength and the weakness of 2D materials. They're highly sensitive, so that can be very interesting for application in sensing. They are sensitive to the environment. And so even solvents that in principle you think are harmful, then they become quite aggressive for the electronic properties.
Yes, definitely correct. Yeah, and thank you very much. The second question is about you have investigated the other benzones and also spiral in graphene-based FET or molybdenum sulfide FET. My question is, comparing other benzones or spiral, which is better to get high-performance phototransistors?
Okay, so let's say the azobenzene is, of course, more established. If you look among photochromic molecule, the one that you find more paper that have been reported is azobenzene. Okay, azobenzene, the problem that you have, but this is also a problem of the spiral, that the second state that can be the cis or can be the mero is not thermodynamically stable. So that is not good if you want for application electronics, because after a while it goes back thermally. at room temperature. Spiro, actually, if you want to play with dipoles, Spiro is better because the fact that you have Spiro that is neutral and the Mero that is actually zweiterionic is such that, that the change in the dipole moment is extremely high for Spiro and Mero. Whereas with azobenzene, I don't think you can reach such a large stage change in dipole moment. And so if you want to play with change in dipole moment as a way to dope your 2D materials, then I would remain with Spiro. Also, Spiro are easy to be synthesized, so it's, this is doable. The azobenzene, of course, if you look at commercially, you find much more availability.
Yeah. Okay, it's a really good idea to improve this kind of performance by use this kind of strategy. It's really great. Thank you.
Also, ASO, if I can add one thing, ASO are slow switches, okay? So if you want to do digital electronics, azobenzene are not very fast switches. For example, diaryletin, that you need to use a different type of mechanism for the doping. This is much, much faster. So we switch on the picosecond time scale, okay? So that is very good.
Picosecond is very fast.
Yeah.
Thank you.
Yeah, thanks.
Okay. Thank Professor Hu. Oh, Ivan, you can open your microphone.
Yeah. Hi, Paolo. Yeah, very interesting talk. I can learn a lot from your very good presentation. And I have one question about the STM image, about Marco Gobbi's work. The STM image on the graphene is quite beautiful. I would like to know, is it very difficult to form the monolayer on the graphene or on the MOS2? And is there any trick to do it? Or about, for example, the concentration or something like that?
Yeah. No, okay. So let's say you have to start from the knowledge that there is a lot of studies done in the last 30 years. For example, also in China, you're president of the Academy of Science. He was one of the pioneers of molecules on graphite, right? At the solid-liquid interface. Then you have Stephen De Fater that has been doing a lot of stuff, Jürgen Rabi initially. So the very same basal plane of graphite is the one that you have in graphene, okay? So, and this takes advantage of the high affinity of molecules for physics-solving on the basal plane, on that basal plane, okay? Now, the only weakness you might have when you play with graphene in respect with graphite is that graphene, typically you produce by CVD, and then you have to transfer on silicon dioxide. And so sometimes it's not super flat as it is, let's say, a bulk graphite that you peeled with Scotch tape. So there might only be a problem of roughness associated to the non-perfect transfer approach. Otherwise, it's the identical surface of graphite, the one of graphene. Likewise, MOS2. I think the major challenge is the one of being able to transfer a large flake of MOS2 onto a flat surface that can be insulating like silicon dioxide. Once this is done, then the generation of a film, this exploits some knowledge that has been developed in the last 30 years. So physics sorption and long alkyl chain or big aromatic system helps to get an extended self-assembled physics or monolayer. So that is doable. I don't see a major problem with this. And then STM can be done in situ. Of course, preparing films that are highly ordered at the solid interface is easier than in dry films. There you have to control a bit more the concentration. But Marco Gobbi showed that this is actually very well possible. There are many other papers about dry films studied by STM that you can find in the literature with using substrate as. So that I think is doable, and it's very important because this kind of study, this kind of STM imaging allows you to correlate the very structure at the atomic level that you have in your, let's say, superlattice with electrical performance that you have studied in the transistor type of device.
Okay. Okay. Thank you very much.
Thank you.
Okay. Any more questions?
李强 can I ask a question?
Hey, Xiaoye. Hey, Xiaoye.
Hello.
From Nankai
Hello, Paolo.
University.
Hi. Hi, nice to see you.
Paolo. Hi, nice to you. So very, very interesting, a very fantastic talk. So I have a very general question regarding the non-covalently functionalized 2D material.
Sure.
So I wonder, is the supramolecular order of soft molecules very important or not? So in which cases you would just need a randomly absorbed molecule, and in which cases you would need very regularly assembled structure?
Yeah, that's a good question. So actually, I think if you want to dope to the material, so let's get wait, this is more clean. If you want to dope to the material, wait, let me go to this slide. So you can actually use, let's say, dipoles, or you can use charge transfer phenomenon. So if you use dipoles, the effect is collective. And so here, if you are looking for a collective effect, you need to have ordered films, okay? If you use charge transfer processes, here you don't need ordered films, okay? I mean, anyways, in my laboratory, since in my beginning of my career, I was doing a lot of AFM and STM studies. We value very highly structures, okay? In the sense that we try to correlate always the structure that you have in your components that compose your device with the performance of your device. Because actually we believe that the reproducibility requires also a good control over the structure. So that somehow is a bit the philosophy of my laboratory.
Yeah,
that you can, and so that, but in some cases, this is less important for the charge transfer approach.
Yeah, sure. Okay, thank you.
Thank you.
Okay. Thanks, Xiaoye.
Hi, Paolo.
Lei Zhang.
Hi, Paolo.
Hi.
It's nice.
Hi,
It's
Lei.
nice to see you. Very
Yeah,
nice.
fantastic.
Very nice talk. I have a question to ask.
Sure.
So when we use Theo group to reduce the 2D material, I mean, I think it is the reduction process plays the role to dope the molecule. So we know that the oxidation or reduction tendency of CO molecules is depending on the acidic or the base environment. So if we can try to tune the pH value to tune the doping the doping process.
Yeah, that's a good point. That for sure is a parameter that can be used in order to control, let's say, the acid content for doping effect. That's something that we haven't done it yet, but I think we should try that for sure. That's a very good point.
Yes, when it is in the base environment, I think the tendency to reduce something will become much stronger, maybe. Yeah.
Absolutely. That's a very good point.
Yeah. The other question is, I noticed the device structure we used to tune the response of dual functionality device. Use the ferroelectricity material and the dielectric molecules. I noticed the top electrode is made of gold. We know gold is also opaque, and at the bottom the electrode is silicon wafer. So that structure is encapsulated by two electrodes. So how the light could go through the barriers and go into the active site inside the device.
A thin gold electrode on the top. Okay.
Oh, okay,
so,
okay.
Yeah. So we radiate from the top. That was the reason why it was not obvious to me that the light could penetrate to the photochromic layer. And so that this demonstration, this demonstration here on the left was very important because it proved that it does work. And we did the same also for the spiral pattern. So that's I've seen that she did this. She did a fantastic job. But I like it because really this Janus approach allows really to diversify the properties. You can think of putting different type of responsive unit that respond to other stimuli. This is what we are doing in my laboratory at the moment.
Yes, it's a very pretty design.
Yeah,
okay, so thanks, Paolo.
Yeah, thank you very much.
Okay, any more questions?
Yeah, Professor Paolo, a wonderful talk. Yeah.
Thank you.
Professor Delta.
Because I think the time is very long, so I'll ask one small question. For the 2D hair structure, some of the 2D material are produced by CVD method or other by the exfoliation method. Have you studied the effect of the preparing method for the property of the hair structure?
No, frequently we use the Scotch tape one. So let's say the CVD is used only when we need to have a very large flake, for example, for doing STM or for doing optical studies. But typically for the device studies, we use the Scotch tape also because, let's say, access to a good tungsten diselenide that is CVD is a bit complicated, okay? Actually, there is some good coming from China, but now with COVID, all the parcel coming from China, they are super slow, okay? So it takes too long, you know? So we have to find a European solution because, there is a problem with post.
Okay, thank you, Professor. Thank you.
Thank you.
Okay, maybe Paolo, I ask the last question.
Sure.
You can, in your lecture, you show you can tune the polarity of the two-dimensional materials. So do you think it's also possible to open the band gap of some two-dimensional material by the strategy you used? Do you think it's also possible to some kind of organic material?
You mean graphene?
Well, the idea is with a very strong dopant, this should be feasible. So it's we tried as well. This was about 5 years ago to use molecules to trigger reactivity and to cut a ribbon, but this turned out not to be so easy. Okay, so the chemistry was done by Xian Fang in Dresden, and we could not use reactivity to break the conjugation of graphene underneath and to open a band gap. But of course, when you go to transition metal dichalcogenides, the band gap is there because they are semiconductors. So then there is no need to open a band gap. And so that is what we have been doing more recently to skip this kind of step of the absence of a band gap.
Okay, thank you. Thank you. And
thank you.
Maybe Professor Hu, maybe make a conclusion remarks.
Not conclusion. Just we hope the COVID-19 or the pandemic could be over soon, so that we can invite Paolo to Tianjin.
Absolutely, I'm very much looking forward to come back. Really.
Yes.
But in the meanwhile, keep sending me your best students. So
definitely, and also send your best student to Paolo.
Yeah, I will for sure.
Zhang, yeah.
So now is the time that there are this kind of CSC application. If anyone is interested to come for a PhD in my group, don't hesitate to contact me.
And CSC still we can, all students can apply for CSC support. Yeah. But now during this pandemic, a lot of students and also their parents would like to keep them just stay in domestic.
Yeah, I know. Mobility decreased.
Yeah.
Mobility decreased, but it is also a psychological obvious reaction, you know. So
yes,
we understand.
I'm sure. Yeah, if there's a pandemic is over, for example, the end of this year, probably next year, a lot of students would like to find a possibility to work or study abroad, especially in your group for Paolo.
Absolutely, you're all very welcome.
Okay, thank you very much for your excellent talk again, and hope we can meet soon. Yeah,
absolutely. In the
meanwhile,
and
Professor Huang,
thank you, Paolo. 谢谢胡教。
do you like some comments or some words to Paolo?
Yeah, very nice work. No more comments because more people, many people already ask questions already. Yeah.
Great.
Okay. Thank you. Thank you again.
Thank you very much.
Thank
you.
Thank you, Paolo.
Thank you.
Bye bye, everyone.
To China in the future.
Paolo.
Bye bye.
Take care, everyone.
Yeah, absolutely.
Thank you.
再见，张老师。
Yeah, bye.
李师弟和一帆师弟。
Thanks.